Swings, often seen as a simple childhood pastime, are actually a perfect example of pendulum motion, a fundamental concept in physics. Throughout this course, we've learned about the principles of potential and kinetic energy, oscillation, and damping. Today, we'll see how these concepts come into play when we take a closer look at swings.
As you swing back and forth, you experience the exchange of energy between potential and kinetic energy. At the highest point of the swing, your potential energy is at its maximum, which then converts into kinetic energy as you descend. Does the mass of the object at the end of the pendulum affect its period?
No, the mass does not matter. This is because while a larger mass would be more impacted by gravitational force, it would also have more inertia. So, when angular displacement is small, any mass would have the same period.
The length of a swing's rope actually plays a crucial role in determining the amplitude and period of the swing's motion. Longer ropes allow for larger swings, while shorter ropes result in quicker swings.
You can also see this trend in the simple pendulum equation. If the quantity L increases, the period also increases. For example, if a swing had a rope that was 1 meter in length and we assume the acceleration due to gravity is 10 meters per second, then we get a period of 1.99 seconds. This means that it would take 1.99 seconds for the seat to go from a resting position to both ends and then come back to the initial position. But if we were to increase the quantity of L to be 2 meters, then the period would increase to be 2.81 seconds.
By adjusting the length of the rope, we can observe how it affects the swing's motion, illustrating the principles of pendulum motion in action.
But swings aren't just governed by pendulum motion, they also exhibit damping effects. Air resistance and friction gradually reduce the swing's amplitude over time, eventually bringing it to a stop.
Understanding damping allows us to analyze how external forces influence the motion of swings and other oscillating systems.
The history of the pendulum traces back to ancient civilizations observing the swinging motion of objects suspended from fixed points. However, it was in the 17th century that the potential of the pendulum as a precise timekeeping device was realized. Galileo Galilei is credited with observing its regular motion, and Christian Huygens invented the first practical pendulum clock in 1656, revolutionizing timekeeping.
Pendulum clocks became widespread in Europe, but were eventually superseded by more accurate timekeeping devices. Despite this, pendulums continue to be studied and utilized in various scientific disciplines for their elegance and predictable motion.
As we conclude our study of pendulum motion, I encourage you to continue exploring its applications in the world around us. Whether it's on the playground or in the lab, the principles we've learned will continue to inspire curiosity and discovery.